Can y'all see my screen okay?
Yeah.
All right. So he said that your professor is a he, right?
Yes.
Okay, so he said he was going to ask some questions about just kind of semiconductors in general and diodes. It's kind of based on vocabulary, so I have some questions here that I thought we would look at and talk about. And I'm going to be relying also on y'all to help me out sometimes, because like maybe y'all use a different model or something, and so when I ask a question, please feel free, or please do answer, and give me whatever information you have. Okay, so let's just start and do participate as well. So let's start with number one. True or false, silicon is a compound semiconductor made by combining elements from different groups of the periodic table. Is that true or false? Should be an easy one.
False.
Yeah, that one's false. Silicon, of course, is an element. Um, and why is silicon why does silicon make a good semiconductor?
It's like something to do with the valence and conduction bands.
Mm-hmm. So silicon, just like carbon, has 4 electrons in its valence group, and when one of those electrons gets free, it can move around and it can be a conductor. I mean, it makes it a conductor, but then also the hole that it leaves behind. It's weird to think about the hole being able to move around, but the hole also moves around and also can conduct a current, and then you can adjust the properties in different sorts of ways that we'll talk about in a minute. Okay, so true or false, at absolute zero, intrinsic silicon behaves as an insulator. Any ideas on that one? What happens at absolute zero?
There's like no movement at all. No energy.
Yeah, there's not going to be any motion, and so if there's not any motion, then you're not going to have the electrons moving, and so then yes, it is true, it does act as an insulator because you can't have any conduction. Okay, true or false? Doping a semiconductor increases its conductivity.
Say
So
true.
that is true. So what do you dope? Let me see if this comes up. It doesn't. So what do you dope a semiconductor with?
It's either like boron or phosphorus.
Good. And so boron or phosphorus, and the reason for those is boron has 3 electrons in its valence, and phosphorus has 5 electrons in its valence. And so that means that phosphorus has an electron that it can contribute to the conduction, and boron has a hole that it can contribute. And so it's the doping that really adds to the conductivity of a semiconductor. Okay, true or false? In N-type silicon, holes are the majority carriers.
Um,
So I remember
aren't holes positive?
holes are positive, yes.
So I'd say no.
Yeah, and that's right, and that was the right reasoning too. Holes are positive, and the N is negative, and so they are not the majority carriers. Now, okay, here's a question for you: Is we're talking about these electrons in those holes? Is Silicon, is the silicon charged? Does it have a charge? The answer is no, it doesn't. You still have the same number of positive and negative charges, so overall it does not have a charge. It just means that there are charged particles or charged parts that are able to move around, but overall it is still neutral. Okay, number 5, true or false? In p-type semiconductors, doping introduces more electrons than holes.
I guess it depends.
Okay, so why would it depend?
Just on what you're doping it with.
Well, it's a p-type semiconductor, so that's going to tell you what type you're going to dope it with. So a
Okay.
p-type means you're going to be doping it with something like boron.
So basically, we're just like, for example, donating something, like donating an element to the another semiconductor.
Yeah, so the way it works is you have silicon, 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 and each of these is covalently bonded to 4 around it. And just on its own, every once in a while, one of these electrons, say the electron from this silicon, will get free and it will be able to travel around. But you'll do much better off if instead of having all silicons, if you introduce an impurity, and depending on the type of impurity you introduce, it'll either introduce more holes or more electrons. So if I introduce, say, boron, so let's say I replace these with boron, so boron, just by nature of its valence, has a hole in it already, so it doesn't have to lose an electron to have a hole. And so what can happen is an electron that's free from somewhere else can travel and hop into here, and then you have a hole right here, and then another electron can hop into there, and then you have a hole right there. And so the holes can travel like that. And so introducing boron would introduce holes. And on the other hand, if I introduce phosphorus, I would not do this in the same semiconductor, but let's say I introduced phosphorus. Phosphorus has 5 valence electrons, so it introduces its 5, and then it already has a free electron that can go ahead and go travel to some hole somewhere. And so introducing phosphorus introduces more electrons. And the phosphorus, that would be an N type, and the P type was the type with the boron. And so going back to this question, in p-type semiconductors, doping introduces more electrons than holes. That is false. It introduces more holes than electrons. Okay, did that make sense?
Yes.
So what did like are we able to just use any element we want to dope a silicon with?
No, not really. Um, so the best ones to use would be something that is trivalent, 3 electrons, like boron, and that would give you p-type. Or would you say pentavalent? I don't know if you would or not, but I'm going to say it. Pentavalent, 5 electrons, like phosphorus, and that would give you an N-type. And hold on just a second, let me see if my knowledge is correct there. I don't want to tell you something wrong. Let's see. Most common types of doping atoms are donor atoms like phosphorus, arsenic, or antimony, or which create N-type semiconductors, and acceptor atoms like boron and aluminum, which create P-type. So, and that's all I know about it. So that's the extent of my knowledge. So, but it wouldn't do any good in terms of being a semiconductor if you didn't dope it with something that would change this property of having excess holes or electrons. Other questions? All right. Number 6. The conductivity of an intrinsic semiconductor increases with increasing temperature. Another way of saying this, same thing, is the resistivity decreases with increasing temperature. So those two things say the same thing. Is that true or false?
True.
It is true for everything but semiconductors. It's actually false for semiconductors. So semiconductors get lower resistance as they get hotter. And that's unusual. That's not the way most things work. The reason it's true for semiconductors is by the nature of their conductance, how their conductance works. So, unlike metals, which just have a sea of electrons that are free to move around, and that's why they are conductors, semiconductors conduct through this process that we talked about with the holes and the free electrons, and those are able to move faster when you have a higher temperature, and so the conductivity gets higher. So they are unlike all other materials in that they get less resistance as they get hotter, and that's not true like with a resistor. If you go to the lab and you have a resistor and it gets hot, that resistor doesn't work anymore. So that's different. All right. Majority carriers in a p-type semiconductor are free electrons. So
Would it be holes?
It would be holes, right? And so it's majority carriers. So we say majority carriers makes it seem like there are more holes than there are electrons. Overall, it balances out. It is not charged, but the electrons are bound, and the holes are free to travel in a p-type. And in an n-type, the most of the positive charges are bound, and I forgot which type I was talking about, so I'm just going to stop. But the majority carriers in a p-type are holes. Now, the next one you should know because I've been talking about it. What is the term used to describe the process of adding impurities to a semiconductor to change its electrical properties?
Doping.
That would be doping. Do holes or electrons travel in the direction of conventional current flow? Or in other words, if I draw a circuit and I have the current, and that's the direction of conventional current, and so I've got some direction associated there. Do holes or electrons travel in the direction of conventional current flow?
Holes.
It would be holes, because when we draw a current, we're acting as if we have positive charge carriers going. So the direction of the current is actually opposite the direction of the electrons. And so if we talk about conventional current flow, that would be holes. What are two main mechanisms for current flow in semiconductors? So in other words, why do we get current? What is driving the current? So two mechanisms for, what did I say? Current flow. So what is it that's making these charges travel?
An electric field.
So one of them is an electric field, and so electric field, and that also that we call that drift. So the mechanism is the electric field, and we call that drift, and we have another one.
The current going across it.
Yes, and that is called diffusion. Actually, so if I'm going to do this in the same order, that's called diffusion. Two F's in diffusion. And that is due to concentration gradients. So you would have one side would be p-type and one side would be n-type, for instance, and so you'd have different concentrations of the charge carriers on the different sides, and that gradient would be the what would make them travel. And what is breakdown?
Is that when it's too hot and then it can't the like voltage comes out of it?
Well, don't. It's not really temperature. It's when. Okay, so what is the whole point of a diode?
To like protect the circuit.
It can be.
The current can only flow one way.
The current can only flow one way. So if this is my diode and I have a higher voltage on this side than I have on this side. Thank you. If I have a higher voltage on this side than on this side, then the current can flow. And depending on what model you're using, you might or might not talk about the resistance or voltage of the diode itself. If I had a higher voltage on this side than on this side, then it's not supposed to flow, and I'm supposed to have an open circuit. But if I make that voltage difference too big, or big enough, then you'll have breakdown and current will flow. So that's what breakdown is when current flows the direction opposite the way the diode is is designed. And we call this side of the diode the anode, and this side is the cathode. Have y'all done Zener diodes?
Yes.
Okay, so what is a Zener diode? Well, a Zener diode is a diode that is designed to operate in its breakdown region. So what happens with a Zener diode is it operates like a regular diode um, in this direction, and then in the other direction it will also act like a regular diode up to a certain voltage difference. And so for a Zener diode, it's around 5 or 6. If you have a if you have a voltage difference on this side, from this side to this side, like let's say this is 4 volts and this is 6 volts. No, this is 2 volts. This is 4 volts and this is 2 volts. You're not going to have any current flow. But if you have on this side 9 volts, and so the voltage difference gets big enough, then you'll have breakdown, and the Zener diode is designed to have to keep a voltage in the other direction. Okay, now the next question I have for you is one that I kind of just I need to know the answer to because I don't know what y'all have done. So hold on, let me get that question. Describe the models of diodes you have used to solve problems about diodes. So what models have y'all used?
I have a quick question.
Yes.
In some of the problems we've been asked, it says use ideal diodes. Is that just it doesn't have like a voltage across it, like 0.7, it's just like 0?
Yeah, we'll do. I'll do an example of that right after this, since you asked. So yeah.
Okay,
Okay.
thank you.
Okay. So that'd be one model. So ideal. I would call that a model. I'm not sure what y'all have, but I would say ideal diode. An ideal diode, we would say no voltage drop and no resistance in the forward direction. Oh, pen's not working. Okay, so what others did y'all use?
Voltage drop and exponential.
Okay, good. All right, good. That's what I was hoping. Okay, voltage drop. Y'all didn't do Schlotsky?
It was mentioned, but I don't believe we really went in depth, did we?
Okay, so the exponential is almost the same as Schlotsky. It's just modified in just a little bit, and uh, so yeah. So okay, good. All right, so let's talk about what each of those things mean. So I'm gonna draw a get an example. That's not a Zener diode, I just couldn't draw a straight line. And let's find, I would like to find V here and I here for using each of our three models. So our first model is going to be ideal. And so in ideal, um, we need to determine if the basically if the diode is on or off. If you have more than one diode in your circuit, you have to try different combinations to see, well, which one actually makes sense, which one works. And so if but I just have one diode, so I just have to determine if it's on or off. And it's going to be on if V, the voltage on this side, is higher than ground. So I just need to determine if that's the case. And so I look at this and I say, okay, if I'm using the ideal model, then what's going to happen is I have this circuit is essentially the same as that if the diode is on. So I'm going to assume that it's on, and then I'm going to work the problem and then see if my assumption was correct. So my 18K and my 4K are in parallel, and so my equivalent resistance between the two of them is 18 times 4 over 18 plus 4, which is 3.2727. And so this is equivalent to a circuit with a 3.3 kilo ohm resistor right there and a 6 kilo ohm resistor. And so I could do voltage division. And so if I wanted to find out what V was, V would equal 12 times 3.3 over 6, which is 6.6. So I get that I have 6.6 volts right here. And so then I ask myself, does that consistent with the diode being on? And the answer is yes, it is, because I have a higher voltage on the anode side than on the cathode side, so that is consistent, and so that works. And so now that I know that, I can get the current that I was looking for right here, and so the current through the 4 kilo ohm resistor is going to be 6.6 volts over 4K ohms, which is 1.65 milliamps. Okay, so that is assuming it's an ideal diode. So any questions on that?
Quick question. So you would say this is one of a good, well, not say one of approach, but like one of the approaches to like check if the diodes is on, if there's just one or two.
Say it again.
Would that be one of the ways to approach an ideal diode to like see if it's on with like
Yes. Yes. See if it's on. Assume that it's on and then see if it's consistent with that. So, like, I mean, if I had this, for instance, let's say I had, oh, probably. Did I do the voltage division wrong? I, uh, yes, I did do the voltage division wrong. Yeah. So it'd be 3.3 over 3.3 plus 6 over 9.3. Why do I just make up problems on the, like, I just decide to make up problems? I don't know. And I get 4.25. Did you get 4.25? 4.3 volts. That'd be 1.1. And then I said millivolts, 1.1 milliamps. What's the question? Thank you. Yeah, so the answer to the person who asked, yes, I'll be posting this. If you are not in Circuits 2, send me an email. Probably easiest to send it to my Gmail. I get it quicker. So I'm going to post the recording in the Circuits 2 SI, but if you're not in Circuits 2, send me an email, runne2 at lsu.edu, and I'll send you a link to the recording. Yeah, and yeah, the reason that I didn't tell anybody about this earlier is I'm just doing this for fun. Nobody's paying me to do this or anything. It's just I had some people ask me, and so I was trying to decide if I could do it or not, and I was worried because it had been so long since I had taken electronics, and so I just decided, I just kept kind of putting off like sending on email. So that's kind of on me and kind of not on me. I mean, uh, so so yeah. So anyway, but yeah, I will post this. Okay. So let's say I had 3 volts here, and let's see. Oh, I don't know. I'm just gonna make something up. So 3 volts here, and a diode, and 5 volts here, and a diode, and we're going to ground, and this is 1 kilo ohm. And I'm trying to determine which, if they are both on, both off, or if one of them is on and one of them is off. And my gut feeling is going to be that the one with the 5 volts is going to be on, and the one with the 3 volts is going to be off, and that's my gut feeling because just we've got the higher voltage difference there. So I'm going to start by assuming that and if that's the case, then I would have, this would be my circuit, it would look like that, and I would have 5 volts here, and that would mean that I would have 5 volts here. Oh, hold on, my tablet's not plugged in somewhere. So I'd have 5 volts here, and so that means that this is reverse biased, and so in fact this one would be off. And so I made a good guess the first time around that yes, this is the way it is, with this diode on and this one off, and this one forward, but this one in forward bias and that one in reverse bias.
Can you explain, like, if we were to guess wrong, like if we did say that the 3-volt source was, or like the other diode was on, like how that would be
Sure.
wrong?
Okay, so let's do that. Well, this would be difficult. Okay, so to start off with, it'd be difficult for them both to be on, because if they were both on, that would mean this was 3 volts and this was 5 volts, and they are in parallel, and they have to have the same voltage. So at least one of them has to be off. But let's say that to make this so that that's maybe not the case, let's put a little bitty resistor in here. So let's put this one, so this one was 1 kilo ohm, and let's make this one 100 ohms. And so now this would not necessarily be at 5 volts, so we don't know what this is right now. Okay, so now we can either assume that they're both on, or that one's on and one's off. So I'm going to start by assuming that this one is off, and I'm just assuming that way. And when I do that, I get that I have 3 volts right here. So this is 3 volts and this is 3 volts. Well, now I see that, well, no, that doesn't make sense for the 5 volt, for this diode, for diode 2 to be off, because I have 5 volts on this side, on the positive side, and 3 volts on the negative side, and that's enough even in the voltage drop for it to be on. So it doesn't make sense for it to be off. So now let's assume they're both on. I love it when OneNote decides it thinks it knows what I'm supposed to be drawing. Okay, so now it still has to be true that I have 3 volts here. So I have to have 3 volts here. So that means that my current through this bottom diode has to be 5 minus 3 over 100. Which is 0.02. So my current through the bottom one has to be 0.02 amps. And then my current through this this part right here has to be 3 over 1 kilo ohm. which is 0.003. Amps. So now I have 0.02 amps coming here in, and I have 0.003 going that way. So that means by KCL, I would have to have 0.017 going up, but that doesn't make any sense because then I'd have the current going the wrong way through that top diode, so then the top diode would be off. And so they can't both be on. And so it's got to be the case, well, it doesn't have to be the case that they could both be off, but it can't be the case that they're both on. So I think it's the case that just the the diode 2, the bottom diode, is on. And if you just look at it this way, you can see that there's no reason why it would not be on in this instance, because if the top one is off, there's no current coming through the top one and no voltage coming through the top one either. So if I needed to figure out what the current was or what the voltage was here, then I could do the voltage by voltage division, and I could say the voltage there is 5 times 1,000 over 1,100. Which is 4.55, if that's what the question was. So does that make sense on how you would like test them to see if you chose wisely?
Yes, ma'am.
All right. So now I'm going to go back to the one that I was doing before, and we're going to do it with a constant voltage drop. And with a constant voltage drop, are y'all using 0.7?
Yes.
Okay. So VD is 0.7, and so you're assuming a voltage drop of 0.7 across the diode. And one way to do this is, let's see, I have my notes. One way to do this is to actually just redraw it if you find it helpful, and I do. To redraw it and say, okay, well, I'm going to assume I have an ideal diode now, and I have a voltage source of 0.7 volts. And so now what I could do, okay, so what I could do with this one is I could find the voltage right here, I could do a nodal analysis, and going up I would have V minus 12 over 6K, but I'll multiply through by 1,000 and get rid of those, plus going down V minus 18, V minus 0 over 18, And going this way, I would have V minus 0.7 over 4 equals 0. Because this resistor right here, this 4K resistor, and this 0.7 voltage source are in series, so it doesn't matter that one is like coming before the other one. But it's so we have essentially, I mean, it's a constant voltage drop. So whatever voltage we have here, yes,
That's because volt elements in series have the same voltage, right? Is that what you're saying?
same
Or
current, same current,
same current? Yeah, yeah.
same current. Yeah.
Okay.
And you're right. So it works that way. Or I could just say that the current through here, if I don't know what it is there, I know that when I get to the other side of this little voltage source, that voltage would be at V minus 0.7, because that's my 0.7 voltage drop, and then I could just do V minus 0.7 as my voltage there, minus 0 over 4 equals 0. And you would solve for V in that case, and you get 4.6058, I think, if you do it that way.
Does that V minus 12 over 6, does that just, is that saying that like the current's flowing back towards the voltage or the would be voltage source, the 12 volt?
It it is, but it's not saying it really is. So this is nodal analysis, and the way nodal analysis works is you identify currents all coming out of the node. So this is I1, I2, and I3. Now I1 could be positive or negative, and I'm just saying I1 equals V minus 12 over 6. Now, if I1 doesn't go in that direction, if it doesn't actually go up, then this would give me a negative number, which in fact it does. Because once I get my voltage, this is 4 something, then this number right here is negative, and so it means, no, I don't really have a current going up, I have a current going down. But the way nodal analysis works is you say, I'm going to sum up all of the currents coming out of a node and set them equal to 0, because the sum of all the currents coming out of the node has to be 0.
Okay, thank you.
Yeah, now I have noticed, at least when I took electronics, the professor seemed to like KVL better than KCL. I'm not, let's see, so I don't know the current there, I don't know the current there. Yeah, I just do better with nodal analysis, so I'm going to stick with the way that I know how to do it. Okay, now let's look at the exponential model. Oh, I really need these notes, not so much for this problem, but for a problem in a minute. Okay, well, I don't manage anyway. Okay, so you have to have, in order to do this, You have to know something about your diode. Namely, you need to know its saturation current and also its voltage given as VD.